and hopefully university earth sciences too. And I don't know, many of you may have seen this figure here. It's Geoscience for the Future, and it's this need for earth sciences across Australia. And it's something that many of us as a first year university educator use frequently to show the need for geoscientists in the coming decades. And I think Sabine was impressed that we'd managed to pick a Earth Science for Society topic that actually wasn't on this chart yet. So that's what we're going to be talking to you about today. But we're very passionate about promoting earth sciences. And if there's any particularly secondary earth science teachers, so high school teachers here, we're happy to get in touch later if you want us to share this with any of your students. Traditionally, I work with critical minerals, so finding the metals we're going to need for a high-tech future and decarbonised society, whereas Lloyd's more focused on
normally on plate tectonics and on sort of large-scale magmatic systems, and more recently looking at geothermal energy and hydrogeology.
We don't usually work together, but this is a topic that we decided to join forces for. So we read the Sydney Morning Herald. So Lloyd and I are a couple. We're both geoscientists at Wollongong, and we've been reading the Sydney Morning Herald and keep seeing these images pop up and articles pop up that were distressing about the rise of silicosis in Australian stonemasons. So we went to the literature, and out of Australia, so Australia's really leading the way in this, particularly Safe Work Australia and WorkSafe Victoria, and the academics associated with that. And so basically there's horrific stats coming out on this. So this came out in 2023, so last year, and it's saying that of the 544 stone benchtop workers, so the people that install kitchen benchtops in your homes, they think conservatively, and this paper sums up, that about 20% of them have accelerated silicosis in as little as 3 years exposure. So there's something happening in this industry where we have an entirely preventable disease that's prevalent in the industry, and the government has just started this year really rolling out some serious legislation to try and curb this trend. But once you've got silicosis, really it's too late. You can't undo what's in your lungs. So just to highlight that this is really shocking stats coming out of a developed country. And it's all to do with a mineral that I've been working on for the last, 15 years, called quartz. And as a scientist, many of you will be familiar with it. It makes up more than 12% of the Earth's crust. It's common in granites and sediments and all sorts of rocks we're used to. But it's inert, so if it's in, it's totally fine to touch a granite and it won't hurt you. But where it's a problem is if you breathe it in. So the idea is what's respirable can harm you. And I'll go into that a bit more in a moment. But the idea is that you have, it has to be crystalline silica is what's legislated as having a lower workplace exposure standard. So you can only be exposed to very small amounts of airborne crystalline silica to stay healthy. And if it's not crystalline, so it's amorphous, like this structure up here, like in a wine glass, although that's technically glass, but you can have amorphous silica in a variety of forms, and it's thought to be less toxic than crystalline silica, and we'll come around to that in the talk as well. So in a nutshell, what happens is, and if many of you are geologists and familiar with sedimentology, so the idea is that the bigger the grain size, the earlier it drops out in the upper respiratory tract here, and the finer the particles, the further they go in your lungs. So the particles that you breathe in that are really, I say coarse, we're talking more than 10 microns, can more or less mostly be processed by swallowing. So if you breathe in particles that are more than about 10 microns, most of that can be removed from your airways by just mucociliary clearance, which is just swallowing. The problem is when these very fine particles, which are 5 microns to 10 microns or less, but there's a range of sizes. There's not just one size, there's a range of sizes that are bad for you, but basically the finer it is, the harder it is for your body to clear, because it can't be cleared by swallowing, so it has to go through these little cells called macrophage and cleared through your lungs that way. And for whatever reasons that we'll get into, it's harder to do with quartz. Silicosis, of course, is entirely preventable. You can not get it by not being exposed to it or reducing your exposure to it. So we've known about this in society for a long time. It was documented in quarry workers about more than 400 BC. And as recent, well, as early as 20 to 79 AD, Pliny the Elder documented people using respirators from animal bladders. So we have known about this for a while. The prevalence is, of course, worse in developing countries where they don't have the legislation that we're lucky to have. So while we're talking about it in Australia, but of course, this is even more prevalent in and definitely less well documented in other countries. I'll pass over to Lloyd.
All right, so yeah, we, I guess, started to think more about this last year as there was discussions by politicians and the regulators on bringing in controls on how to restrict or limit the use of this material. And I suppose we were fortunate that Wollongong Uni was trying to encourage different faculties to work with one another and providing some funding to stimulate that. And so we paired up with some of academics in occupational health and safety to look into this problem in more detail. I suppose really what got us looking at this was that the talk about a ban of this material first started to talk about material that had banning material that had more than 40 weight% crystalline silica. And I suppose as geologists, we were kind of thinking, well, what would that relate to in terms of natural stone? And that seems like if it was equally applied to natural materials, then there would be quite a bit of natural dimension stone that should also potentially be banned. So
yeah, basically the very first legislation that was coming out of Victoria on this was saying if it has more quartz than granite, we should be regulating it more heavily. And what got me like a bit jumpy was that there were various numbers people were proposing for how much quartz was in a granite. And as an igneous petrologist, like, we know that quite well. And none of those numbers were matching what a geologist would say. So in the policies that were coming out, they were saying a granite can have between 2 to 40% crystalline silica, 10 to 40%, depending on what you were reading. So yeah, I found that distressing.
Yeah, so as of July this year, the government brought in a national ban on this engineered stone materials. Yep. And so, I mean, this is basically what's been happening since we spoke about this in March. So the government brought in a ban from the 1st of July on the manufacture, supply, import, processing, and installation of material with more than 40% at that time, was it? Or?
No, they've banned engineered stone completely now.
Yeah.
So anything, and we'll go over that in a moment.
And then from September 1st, there was a stronger regulation that was coming in force, which included anything with more than 1% crystalline silica in it. So it's not necessarily a ban on things that are more than 1% weight crystalline silica, but stronger controls on workplaces that are processing on materials with any crystalline silica, basically. And for me, managing a lab that crushes and cuts and does all sorts of stuff with all sorts of rocks, then that stuff also is something that universities need to consider in terms of their health and safety documentation and processes. So as well as this kind of grant that was kind of a push for us from the university, and I were routinely driving through Padstow and seeing the various engineered stone workplaces through there, and we were thinking, what could we do to help as a geologist to sort of get involved in this debate and help to inform future policy decisions. Do you want to?
Yeah, so I guess the key questions we're going to go over in this talk is what's in engineered stone. So that was the first question we had. What is this stuff that's so toxic? What's in this material that's killing people? Because, you know, when we teach any sort of first year class, we talk about rocks being aggregates of minerals, and synthetic rocks are pretty much no different. They just have resin as well. So we wanted to know what minerals were in these things. We wanted to know how that compared to natural rocks. Are there natural rocks we should be more worried about than others? And is there something that might make engineered stone more toxic than natural rocks? So that's what we're going to do.
Yeah. All right. So this came from the two of us, I suppose, also being involved in home DIY at various points, as well as managing labs and things like that. So what could we do that is?
Yeah. I think what surprised us about this is how ignorant we were of silicosis throughout this process.
That's true.
As geologists.
So by definition, engineered stone is an artificial product that contains crystalline silica. This is using the definition by Safe Work Australia. It's created by combining that material with other chemical constituents such as water, resins, or pigments, and it undergoes some process to become hardened. So that might be some heat treatment or basically various things to let the resin set. Under the legislation, it doesn't include concrete, cement, bricks, pavers, ceramic, porcelain, tiles.
So they're not banned, but they're now regulated.
Yeah.
If they contain more than 1 weight % crystalline silica.
Yeah.
And then dimension stone. Again, something I was reasonably ignorant of as a geologist. But the idea that what is sold as granite is not necessarily a granite. So that was one of the things that had been confusing me. So in dimension stone world, it's how the material behaves. So a granite, so something that might be sold in a kitchen store as a granite could be a granite, a gneiss, a labradorite, a gabbro, or basalt. But of course, as geologists, we know they have wildly different quartz contents, and that we need to think about that with how they might be toxic or not. We'll also focus a little bit on marbles, briefly touch on limestones, and of course the quartz-based dimension stone groups such as sandstones and quartzites. All right. So the obvious thing is, if you want to know what's in the engineered stone, the first thing you should do is look at its material safety data sheet. So why are we going and measuring this stuff? We could just read the safety data sheets. And it turns out with these products, they have really, really vague safety data sheets as someone who's worked in labs before. So it says, for example, one product you could look up, and we're talking about these products that have now been banned, but it said it contains somewhere between 40 and 92 weight % quartz. So that's a really different number. And there's lots of studies that have been done too about cutting rocks and the volume of crystalline silica produced when you're processing these materials. But very few, in fact, there's only one study we're aware of where they've actually measured the quartz content of the substrate. So this is where Lloyd came in, running an XRF and XRD lab.
Yep. So we thought we'd make use of the labs that we're running to look at this, because the labs and the equipment in them is perfectly designed to answer these questions. So we went a little bit nuts, or I went a little bit nuts and was dumpster diving at stonemasons and requesting samples of different material to use. So we assembled a bunch of samples, 92 or about 100 samples of engineered stone from 8 different suppliers. This included the sort of old school, like really 90% crystalline silica material, as well as some of the things that were proposed as low silica variants, which at the time was about things with 40% or less than 40% weight % crystalline silica. Range of colors and textures. We also put some porcelain tiles in, which is one of the alternatives that's been proposed. and some natural dimension stones as well to get an assessment of what that material was in comparison. So this is just a snapshot of one supplier of different variations of what the engineered stone could look like, with relatively, I should have updated this, but the various X's were meant to indicate the percentage of the silica, silicon oxide, and the crystalline silica content. But basically all of this material is from this supplier is about 85 to 90% SiO2 and crystalline silica as well. We chopped up the rocks, washed them, ground them into powders, melted them to turn into glass beads and into press pellets, so we can look at their elemental composition and their mineral makeup. In terms of the SiO2 contents, all of this material is pretty much dominated by high amounts of SiO2. The LOI number there just means the loss on ignition, and this basically equates to how much resin is in the sample. And you see there's some variation in supplier 6, which is one of the low silica variants, where they had some other minerals in there, which some calcium and magnesium bearing minerals, and the porcelain tile as well, which had higher amounts of aluminium oxide relative to the other samples. Slide. Okay. Yeah. Sorry. Basically, this equates to just the breakdown in what the mineral content is of the samples. So, pretty much glass. Dominantly quartz, glass, and resin, and some with slight variations in some other minerals, often for pigments or some slight changes in color. There's been some work from one group that's kind of working on this material, who claimed that there was high amounts of trace elements which were potentially hazardous to, that could be a difference, I suppose, compared to, that might explain why engineered stone might be bad if it's breathed in. Basically, the trace elements of the bulk material are really low compared to most other materials, or definitely natural rocks. The chromium that's indicated here is potentially there, but it's also potentially a contaminant from the crushing process when I've sampled the material, or the crushing process, which is the jaw crushers, basically, that it's going to crush up the aggregate that goes into the engineered stone. And we found little bits of stainless steel and things like that in the material in a bit more detail. The porcelain sample is the only one which is really quite different, which high amounts of barium, which is the glaze that's on the porcelain, high amounts of zirconium, which is related to zircon in, I guess, the glaze as well. So we continued to go to town a little on these samples. We drilled sort of micro cores into a select amount of samples. They're little tiny 4mm cores, and we sent them to UNSW and worked with Patrick Tung there to process the material to look at the grain size variation, and particle shapes and things like that in the samples. And then Dom went to town looking at these under the electron microscope.
Yeah, and I think what came out of all this work, and hopefully you'll see in the CT scan here on the right, and you'll see the same evidence on the electron microscope, is these materials, regardless of what color you pick, whether you get one with fractures and swirls, whatever you order in the catalog, from a material science perspective, they all look the same. It's quartz chips in resin and barely anything else. So we really, we can tell you that it's just a lot of quartz and a lot of resin. But what was, and what we're really interested in, was the grain size and the morphology of these things, because that differs to natural rocks, obviously. So these are some images from the scanning electron microscope. You can see the holes from where Lloyd did the cores. And this is at the edge of some of these drilling sites. And what we're seeing is that even before it's manufactured, so before we cut it with a drill or a stonemason cuts it with a saw or polishes it, these have incredibly small grains to start with. So you start with big chunks of quartz in a matrix of super fine quartz. So here for reference is what you can breathe in quite easily. Anything smaller than the orange bar and anything smaller than this purple bar is going to go into your distal lungs a lot more efficiently. So you can see that the material that is in the resin, the binder, is pretty much very fine quartz flour and resin. So lots of respirable quartz in the actual matrix of this material, which we didn't know before and no one had done before. So here's lots of images. Pretty much they all look like this, these big quartz fragments, and it's sort of fractal with how fine the quartz grains get. They're supported in a quartz matrix. There's tiny little bits of this stainless steel that Lloyd mentioned, which is where we think the chromium's coming from, and I think that's probably introduced in the factory that makes the engineered stone themselves. If you're bored one afternoon, I recommend Googling engineered stone factory on YouTube, and they're interesting, fascinating videos saying how you make a fake rock. But anyway, these are the low silica variants, where rather than just using quartz, they're starting to use these glasses, which are composite materials. And we'll get there in the talk, but we're not sure, you know, that's particularly much safer. And there's also pyroxene in this low silica variant. So of course there has to be minerals supporting this synthetic rock. So they're just, if you're going to ban crystalline silica, they'll use something else. Here's what porcelain looks like. I'd never thought much about porcelain, but I'm absolutely fascinated by it. And you can see that porcelain also has these tiny quartz grains, although they've gone through a different history because they've been baked in a kiln to create a glass and mullite, and what's left of the quartz is, we think, probably these little grains. So not exactly our wheelhouse, but still they have a fair bit of quartz in them. Did you want to talk about particle size?
And so, yeah, this is just saying what Dom had said before. No matter what you look at, they can look different. So the images on the bottom show what they look like as a benchtop. The images above show what they look like under high magnification on the electron microscope. So they all, regardless of these sort of 100 samples that we've looked at, all look like these kind of glacial ice rafts from space kind of thing.
And just to mention that one of the pigments they're using is cristobalite, which is of course crystalline silica in itself. So the ultra pure white is often cristobalite.
Yep. So again, if you zoom into all of these, same again at almost 6,000 times magnification. This is just capturing that, what Dom was saying before, that all of the matrix of the materials is tightly packed, fine grain class in glue, and trying to make some of this myself in the lab. It's surprising how little glue is actually, like how little 10 to 15% resin goes when kind of mashing the grains together. So the really fine particles are there to make the material properties of the benchtop really quite strong and a good material, I suppose, to manufacture.
Yeah, a lot easier to use than natural granites that have fractures and all sorts of imperfections that any natural substance has.
So we, as well as the CT work, we use some of the kind of particle analysis software that's embedded within the electron microscope. And so the colorful image is just showing what the software is picking out as different grains. And we're trying to get an idea, I suppose, of how fine a grain size, or what percentage of the fine grain size is in each sample. So basically everything that's in this box, and it's about 15 to 20% of the sample is sort of within that kind of respirable range before there's actually any processing that's been done on the sample, on the material. And across the 92 samples, we basically see the same thing. So it's again and again, all this material has a relatively similar makeup. And to take this further, I cooked up some of the material in a furnace for 700 degrees for 4 hours and to see what would happen. It melts off the resin, and basically that material stays, I don't know, somewhat intact until you touch it, and then it just crumbles to dust. So we use this as a way to try and explore the particle size beyond the kind of the 2D polished surface of the material that the SEM was giving us. So we crushed this up and then we fed it through a laser particle analyzer. And again, just to document how much of that material is really fine grained. So yeah, about 10% is less than 2 microns. And about 45% is stuff that you can breathe in, but not all of it is in that that particle size that you would be trapped in your lungs. Yeah, so 56% of the material is stuff that you could breathe in
prior to cutting.
Prior to cutting.
So this begged the question, well, if that's what the engineered stone is, should we be worried about natural rocks? And it sort of came back to this threshold idea that the Australian governments were beginning to use policies, particularly in Victoria, where these policies were being developed last year. Like, this is very recent stuff. So here's on the left some of the policy estimates. And I knew that from teaching first year, or being a first year student myself, that to classify an igneous rock, we look at the proportion of quartz, alkali feldspar, and plagioclase feldspar to actually define a granite. So the definition of a granite involves its percentage of quartz. And you can look at the book that defines all this stuff, and they also have recommendations for how many dark colored minerals are in a granite. So you can really subtract that to figure out that there should be 15 to 55% crystalline silica in a true granite. So that, by definition, that's how much quartz it should have if it's not a leucogranite or a melagranite. But I thought that was a good starting place, and I thought, well, what about the other igneous rocks? But then I thought, well, what is this granite that's actually being sold, right? So we also decided to be comprehensive in our analysis and found a free online database that in the EU, you have to say what type of rock it is for it to be sold using like geological definitions. So we did find a database that had that, and we classified hundreds of rocks. Some didn't have classifications, but for the ones that did, we put them in a pie chart. And it turns out that the majority of granite being sold is in fact a gneiss or a migmatite, so a metamorphic rock, and not a granite at all. Which is interesting if you want to know how much quartz is in it, because that's quite variable in metamorphic rocks, because you can have a variety of protoliths. But anyway, 24% is granite sensu stricto, so anything in that box in the and the QAPF plot. Of course, granulites and charnokites are heavily represented in the dimension stone stores and catalogues, as opposed to, you know, what's actually on the Earth's surface, because they're really beautiful and they're resistant to wear. And then, of course, alkaline rocks are used, basic rocks, and anorthosites are pretty common. So another thought I had was, well, like, we'd bought a benchtop, an engineered stone benchtop, because it was so much cheaper than natural rock. So, like, are people still using natural rock? And it turns out that looking at the stats, the industrial stats, yes, absolutely. Over the last 20 years, like, we've gone from using 20 kilotons of granite type dimension stones in pink to about 60 kilotons of granite dimension stones. And this is probably due to population increase. So this is a worldwide trend. So definitely we're still using natural rocks as dimension stone. So here's this idea again of looking at what the quartz content of different igneous rocks could be, and I extrapolated that across the whole QAPF plot. So I colored, so there's some color coding here to try and like limit all the different igneous rock types. But basically, dark blue are silica undersaturated alkaline rocks that has no quartz in them. So really great for benchtops if crystalline silica is a problem. Then we've got silica saturated alkaline rocks, granites in red, well, granites and acidic rocks, I should say, in red, intermediate rocks in orange, the tonalite is this dark orange, and the basic rocks like your basalts and your gabbros in this yellow color. So by doing that, it meant that you could calculate very simply using the igneous rock classification chart, how much quartz should be in each of these different rock types, purely by definition. And that's what it looks like. So there's all those different igneous rocks across the world. And basically it shows that the more quartz-rich varieties can have quite a lot of quartz in them, certainly more than 50%. This dotted line here is that 40% threshold that was what was being used by the governments to legislate a granite. And there was another proposed threshold at about 10%. So that's what they thought was in the range, but this is the range of igneous rocks. And of course, there are some that have really no quartz in them at all because they're silica undersaturated. And so I went further. I couldn't stop there. I couldn't stop at igneous rocks because you have to do metamorphic rocks because they're obviously being sold as granites. So this is there's a lot going on here. But basically up here, it's the granite group rocks on the left. And you can see that they can range from pretty much 100% silica, which if you have a really big quartz crystal and a pegmatite, you could absolutely, in theory, depending on the scale of dimension stone you're sampling or the sample you might take from a pegmatitic rock, could have 100% quartz in it, but it's obviously quite rare. So there's the granite group igneous rocks at the top, and pegmatites are, of course, impossible to define in this definition because they are just a grain size. It's any igneous rock with crystals more than 2.5 centimeters in size. Then we've got the metamorphic rocks, and looking at the classifications of metamorphic rocks and the ratios of platy minerals to non-platy minerals, you can say that they sort of have to have a maximum content of 60% quartz at most, but keeping in mind that they could be overprinted by quartz veins, which could add extra silica. So I proposed a definition where you look at the rock type and then add quartz veins over the top because you can get significant quantities of silicification post-deposition. What really surprised me is that the quartzite has, well, it shouldn't surprise anyone, but quartzite has, of course, a lot of quartz in it, as do some clastic sedimentary rocks like sandstone. So they have technically more quartz than engineered stone that's been banned. So there's certainly some common natural rocks that have more crystalline silica than engineered stone. And when I say engineered stone, this is the stuff that has only recently been banned. So it's now trending to the left. It's down to this 1% is the new threshold for regulation of any rock, the processing of any rock. It has to have less than 1 weight percent silica of crystalline silica in it. And that's actually, for anyone who's done X-ray diffraction before, which is our common technique for measuring this, pretty much below the detection limit of what we'd usually measure. So it's kind of interesting. They've put in a regulation with something below the detection limit of what we'd usually measure. So that's where Lloyd and I'll head in the next few years, looking at that kind of stuff. But I was really fascinated when I started putting together, because this is before this 1% crystalline silica regulation came out. And I was looking at how much quartz is in porcelain, which is quite a lot. You can get, typically 10 to 30% quartz in porcelain, and it's dependent on the temperature you fire at. You reduce at the higher temperature you go. Then we've got mortar, so the stuff that in the grout that holds the porcelain tiles together. And if you're a builder doing tuck pointing, that's incredibly high in crystalline silica if you don't do that at home, basically. And clay bricks, clay pavers, concrete, the lower grade your concrete, the more quartz it would probably have in it. And terrazzo tiling. And I also threw loess in there as well, just to know what we're breathing in, as an average for windblown dust, which is quite high. So even limestone quarries, if they're interbedded with sandy layers, they can get significant amount of crystalline silica in them too. So with all this in mind, and this idea of banning crystalline silica, how does it, is it important or not? If you ban it, basically what you're doing is reducing the quartz content, but if you're not wearing a mask, you're still breathing in lots of dust that can still give you lung disease. So it's a play, so there's different ways to minimize this. You can use wet cutting, you can use local exhaust ventilation on your tools, so that's like a vacuum system on your sanding tools, for example, and we always recommend wearing a mask because that's the most effective thing to do. So then moving on to the very last part of our talk so we can have some time for questions. Is there something that makes engineered stone more dangerous than natural stone? And when we started this, hypothesis is that it was going to be that quartz has cleavage, it has no cleavage, it has conchoidal fracture, and that it's very sharp, just like broken glass, and maybe that's a problem in your lungs. But as we read more about it and learned more about it, we realized that wasn't the case. Just to bring it home, like the idea that quartz is more toxic than other dusts has been known for a long time. This is a paper from 1960. This is a horrible chart where they measured how much dust was in the lungs of deceased workers who died from lung disease. And it turned out that if you were working in a mine that had no quartz in the rock, that you would have about 70 grams of dust in both lungs before it was lethal. And if you were in a gold mine with lots of quartz veins, this is particularly data that was coming out of South Africa, you'd have about 7 grams to kill you. So, the problem with toxicity is you need really awful statistics of it actually affecting people to be able to claim it's toxic. So just what in terms of modern exposure limits, the exposure limits for crystalline silica are 1/200th of what you're allowed to be exposed to for what they call low toxicity or nuisance dusts that are free of quartz. Right, so how might morphology affect toxicity? When I started reading the literature, it turned out that maybe the shardiness, the sharpness of the conchoidal fracture isn't what was the problem at all. And this is actually data that's coming out of drug delivery systems, clever designs of silica nanoparticles in medicine. And the idea that these are the cell membranes that I mentioned at the beginning, these macrophages that process particles in your distal lung that you can't clear by swallowing. And it turns out it's easier for them to ingest spheres or anything along that long axis. And if it's got an aspect ratio that's like a rectangle, it can't ingest it that way, but it can ingest it if it's narrower. So there's all sorts of medicine, biotech going on about what sort of morphology can be taken in through your lungs to enable this process called phagocytosis. So as well as that, there's definitely a more complex issue of surface chemistry that we're also starting to get into. And there's this absolutely contradictory evidence that it's the amorphous silica coating that as you fabricate, and this is as a material scientist, someone who's been doing electron microscopy, we know that when you have a crystal, if you polish it, you get a nano, we say amorphous, but it's not purely amorphous, it's really disordered mineral at the top that you usually have to get rid of before you can get to the good stuff beneath that, which is the perfect crystal. So it's likely that the toxicity is actually being driven by these broken, less crystalline, highly disordered fragments, and we're not sure quite what they look like in terms of these materials that are inducing silicosis. The research in this space is really being driven by design of material scientists looking for really thin silica substrates. But this is something, of course, we're going to get into hopefully in the next few years. And the mechanisms for this, for those chemists in the audience, are the idea that you're breaking very strong silica oxygen bonds. And we don't know, so there's a few proposed ideas for why silica is why quartz is more toxic than other, nuisance dusts, and this is it. But as a mineralogist, there are other silica-rich minerals, feldspars, that, have quite a lot of silica oxygen bonds that would also be broken through this process. So I think we really need to work to understand what mechanisms are driving this toxicity, so that we can predict, as they're making new materials and putting them on the market, what might be more toxic. And then something that we've been thinking about, and why engineered stone is more toxic. So we've talked about the size of the grains, we've talked about the shape of the grains, but it's also the history of the grains. So the number of defects in a crystal is likely influencing this. And there's some early data suggesting that myelinites, so highly deformed quartz crystals, are a lot more toxic than just regular hydrothermal quartz crystals. So we think that this is being driven by the density of quartz dislocations and defects in the crystals. So the idea is that quartz from a granite would be less toxic than quartz from a gneiss, and that both of these are being thrown into a factory, crushed again, deformed again, increasing the number of defects to create engineered stone. So this might be, in very early days, we're still writing this up now, to think that this idea of doubly fabricating crystal is why it's more toxic, perhaps, than a granite. So to sum up, did you want to go?
It's fine. You got one more to go.
Yeah, so to sum up, size, shape, and history of a crystal matter in terms of its toxicity. You don't need to worry about, if you have an engineered stone benchtop installed in your home. But if you are doing home DIY, if it's tuck pointing, if it's, getting the concrete up with an angle grinder, in your basement floor, wear a mask. Wear a mask. Look after yourself, because it really is dangerous and you can't undo these things. So we don't understand the toxicity of rock-forming minerals well enough. We have to rely on data of people that have died of lung disease and looking at what minerals they're exposed to post-mortem. We're trying to flip it and predict toxicity of minerals, which is new to this field. And loopholes are going to abound. Once you ban something, new materials are going to come in. So just down the bottom, here are some of the big companies that sell engineered stone, and you can see how vague their new material safety data sheets are. So the aggregates they're using contain, recycled glass, and that can mean a whole lot of different things. It doesn't define the chemistry. Glass is amorphous and by definition like a variable in composition. So they also talk about, there's one product that's marketed as just having amorphous minerals in it, which could contain all sorts of who knows what. So that's, where we're headed next. All right.
Yeah.
So I guess we'll open the floor up for questions.
Wow. Yeah. Fantastic talk. That was really, really interesting. Thank you for that. So the floor is open for questions. Feel free to post something in the chat or jump in just with your voice, or feel free to raise your hand too. While you're kind of pondering that, I found it quite interesting. I think you touched on it at the end, but yeah, it's interesting why silica, why quartz. When there's lots of silicate minerals like feldspars. Can you touch on that again, on what exactly the difference is?
Absolutely. So the research states that it's the freshly fractured surface of quartz that makes it dangerous. So and they've done these amazing experiments where they grew tiny, tiny hydrothermal quartz crystals and, got rats to inhale them. And they weren't as toxic as those same crystals of the same grain size where they were crushed, fractured. And so you need a freshly broken surface to make the quartz more toxic. That toxicity also reduces the longer it's exposed to humidity. So presumably you're coating it in a, silanol coating. I just saw that in the chats. I'd always thought it was the sharp fracture of the quartz that's the problem. And earlier in March, when I gave this talk, I was convinced that was still the answer. So it's good to know that, I'm not too old to change my mind. But And someone's asked if there's a threat to opal miners, and this is exactly what I want to know, because my hunch is if it's breaking silica oxygen bonds, there should be no difference in toxicity to amorphous silica. What is different is that the historical data we have about mining amorphous silica is from a very limited source. It's from, and amorphous silica has so many different forms. So you can have these low temperature amorphous silica spheres, what's it called in the lab, Ludox. And so basically anything with sol gel processed. But the fumed silica, any amorphous silica formed at high temperature has these tightly streamed 3-membered silicate rings that are easier to pop open and form silanols, so they're more toxic. So even within amorphous silica, there's what they call the variable silica hazard. So some forms of amorphous silica are more toxic than others. And because no geologists have been working on, or very few geologists have been working on this project like this in this sphere today, there's no ranking of, how important the history of a grain is and how different the mineralogy can be in amorphous minerals that all fall under the same, bracket in a workplace exposure sheet, if that makes sense.
And I think too, with your question, Jonathan, it's not quite clear why they don't use feldspar instead of quartz. It's looking through patents and things that have come out to design the materials. The patents usually are, or often kind of are a grab bag of like, we'll chuck whatever in there, like so it can include any sorts of minerals, and I think that's partly probably how a patent might be designed to kind of say, well, we want it to include a whole bunch of materials so we can claim ownership of that.
But I think that the feldspar stain, so we're talking about bench tops and really highly practical things. And I don't know if you've ever spilled turmeric or curry on like a bench top, but it just sticks a bit. Like, certain things stain more. And feldspars can have micropores in them as they weather, and they don't have to be very weathered to have micropores, but it might, they're just not as resistant to weathering as quartz. And so they're probably, might have different aesthetic properties at the end of the day. But ideally, this is what, you'd hopefully have some mineralogists advising what might be safer minerals, but we don't really have that data yet.
And Simone, is a question about a threat to opal miners. Then yes, I guess there would be a threat. It might not necessarily be from the opal itself, but it could be from the clastic material around the veins, which is rich in quartz. Basically anywhere where there's dust, it's a potential problem. So you want to limit what dust you're breathing in. So any ventilation systems, face respirator or a mask, whatever you can do to limit that.
Yeah. And tunneling is particularly dangerous, like in the opal mines, because if you're, say, drilling concrete outside and you've got a breeze, lots of the dust will be carried away by that breeze. So I think that's why it's focused, this community of kitchen benchtop workers, it's quite specific, but I think it's because it's indoors. And that if you're in landscaping, for example, that it may be reduced silica load in your lungs purely because there's a breeze about and it's not in a confined space.
So I suppose if you is it necessary to have those? I mean, this is more of a manufacturing question. Is it necessary to have those little micro bits of silica around those larger grains? Because I suppose if you just kept it to the larger grains, it should be relatively safe.
Well, yeah, and that's what we've been thinking about. But I think it's that tight packing of those microclasts, nanoclasts, I should say. And like you saw, we use different techniques, CT, scanning electron microscopy, because we kept butting up against the resolution of what we could actually image. We think, like, I should have taken it to the synchrotron a few weeks ago, because I really think that the finer we go, the finer those particles will be. And they are what make the rock so strong. So they're what make it a great product for, ignoring health issues. Like, as in terms of material science, they give it fantastic properties. It's so homogeneous in all angles. Yeah.
So considering that, it's interesting that masks are effective then.
That's true. Yeah, and I guess we all know a bit more about masks after COVID, don't we?
Yeah.
I guess it's about limiting the load in your lungs. So you're just always trying to cut down on how much you're breathing in. And none of these techniques, as long as you're doing it, are 100% effective. Certainly, even the use of wet cutting, right? It really helps when you're doing the experiment, measuring how much quartz you're exposed to. But as someone who's worked in a rock lab for a long time, you come in and it's dusty because the water's dried out. So like, what is that dust going, you know, if it's in a confined space? So there's all sorts of caveats. Are you wearing the mask correctly? Is the mask fitted properly? And
Do you have facial hair? And it's
yeah.
Yeah, and Barney raises a good point in the chat that a lot of drillers don't wear masks, and of course, coarse grains don't stay coarse when you cut them as well. And yeah, I've got some friends in construction, and you know they're carpenters, but they've worked with stonemasons who might need to cut some engineered stone, and they of course all put their masks on. And my poor mate working with the timber framing just in the same room isn't told to do the same. So there's lots of dangers there. I have one last question. Did your work that you presented to us in March, which is of course before the legislation was passed, I think, or at least before the ban. So did your work directly influence that legislation?
No, it's been coming out fast.
Yeah, no, we haven't influenced that, I suppose. Everything I think we're doing is maybe in response to seeing some of that, I guess, that legislation and evolving so quickly, and probably at least we think evolving quickly without any geologist having an input. I suppose it's an interesting thing coming into a field, a sort of health and safety field, and seeing what sorts of things are published, and yeah, kind of reconciling with that, with at least with how things might be measured on a particular instrument, what things people in the kind of health and safety sphere might kind of latch onto as a potential hazard or idea. So yeah, I think everything we're doing is I guess trying to provide some counter arguments to some of the things that are coming out.
Yeah, and I think it's hard because we're like any research project in earth science, you're always on the cusp of understanding the next thing and the next thing and the next thing. But we do have this submitted and it's bouncing around journals at the moment, which is a real shame because it's been held up there for like a couple of months.
Yeah.
So it's not out yet. And I've never had a paper I've wanted to get out faster. And there's another grant that we submitted 10 weeks ago, and we should know by the end of next week, doing the same project, but with these new generation stones. So figuring out what's in the glasses, what's in the, what minerals are coming in. And what are these effects like? Yeah.
I'm very keen to hear what you find there. Is there any other questions? Yeah.
Hi.
Yeah.
Thank you very much for sharing with us and enlightening me on like the toxicity of engineered stone. But I'd like to have a few questions. And the first question is, are you satisfied with the policy change being made, or you think it could be better? And second, if that is the case, is there anything that you feel that we need to do to innovate in order to improve the conditions for whether it is mining or whether it is civil, because I'm a civil engineering student here in UW as well. So, and Lloyd was my student for field geology last year. So yeah.
Thanks, Shinkai. Yeah, so it's a good question. We actually were flipping around throughout the project of whether we liked the emerging policies or not as we were discovering the data. At the end of the day, we want people to be safe. the best way to do that is really beyond us as geologists. But I think the very first policies coming out of Victoria were really great because while we didn't agree with the granite content or whatever, they were really focused on licensing and education. And the population of stone benchtop workers are largely a flux of migrants into Australia. They've WorkSafe Australia release all these documents in a variety of languages now, like since this ban, which is great. But it's really about education and letting people know how dangerous this disease is, and education. So I think, would you agree that? And it's hard to know how it will play out because all the onus is on the employers. So the government isn't really funding any support really in this to help people comply, which is a real shame. I think that because it's not economic, it really changes the cost of products to do everything properly. They'll, eliminate dry cutting, have properly fitted masks for all your workers, have not just these silicosis doesn't show up very well on regular x-rays. You need the really expensive CT chest scans to diagnose it. So it's very expensive to do what needs to be done properly. And it will, I hope what they're doing will limit it, but we really want to eliminate it completely. And so that was the first bit. And then innovating it, I think knowing what are the safest materials to breathe. So what is it in a nuisance dust that makes it less bad than anything else? And the term nuisance dust just applies to minerals that haven't really been looked at and aren't quartz.
Yeah, and the bad thing here is, I suppose the loophole at the moment is that the companies are, instead of putting in crystalline silica, they're putting in, I guess, largely crushed glass. And there's no, or to my understanding, there's no workplace exposure limits, or there's a higher workplace exposure limit on that material. So sadly, it probably will take a few years or maybe a decade before the workers that are working with the new material are starting to get sick, and so it's kind of just kicking things down the road until there's stats that come out, I suppose.
Because at the moment there's only one study documenting like silicosis like cases from Bengal factories in India where they're machining glass and breathing it in, and it had horrific stats as bad as accelerated silicosis, but it's just the one study, not a big volume of literature like they had for mining quartz veins and things like that.
Thank you very much.
And Amber had a question. So
Hi,
great.
Amber.
Hi, so great to see you. I haven't seen Amber a long time since we did field mapping together, but in second year. But absolutely great point about the exposure thresholds being on the detection limits of XRD. And one of the interesting things about X-ray diffraction is that I've always pressed people before this project about what the limit for detecting minerals in XRD is. And asking who I consider some of the best XRD experts, it usually comes out at about 5 volume%. But it's more complicated than that. So it's the more minerals are in a material, the harder it is to detect lower volumes of things. There's also problems like amorphous peaks. So if you have amorphous things, say recycled glass, for example, in engineered stone or resin, they're going to give potentially signals that block out the quartz peaks. Quartz definitely isn't as easy to identify as other minerals like feldspar that have, really big peaks. So not all minerals can be identified easily. So there's heaps of variables. And Lloyd, did you want to speak about more to that? Hopefully we're having a PhD student start next year to start running a lot of stuff on the XRD to really figure out those detection limits to help inform the legislation.
Yeah, and I suppose considering if there are other techniques that could be used that are maybe doing things sort of in situ or on kind of like looking under the electron microscope and kind of point counting, I suppose.
Raman.
Yeah, so if that would be a better approach, I suppose, than using XRD. So yeah, it might just need us to kind of push boundaries a little bit more in terms of what we can use with the instruments to detect things. And in some ways, there's some materials that could make it easier too. So for the XRD, I suppose just having the presence of quartz in the sample would basically indicate that it's above the 1% limit. So provided that there's no interferences or the amorphous material hiding that, then yeah, I guess we'll learn more hopefully in the next year if our student starts.
Yeah. And another thing complicating this is how you're actually measuring it in the workplace. So we're talking about it would be a lot easier to actually, like the detection limits would be better if you're measuring the slabs of material themselves as they're coming into the country, being imported, sold. But once you've got a busy workplace cutting all sorts of materials, natural rocks, you know, synthetic rocks, then you're reliant on very, very small volumes of dust in a personal monitoring device. And this is what our colleagues in health and safety work with. And so again, we want to run some correlations of controlled studies where we know what's in the benchtop and we know the volume being produced to try and understand those errors and how they relate.
Great. Yeah, so I mean, one very, very quick final question, I guess, is why are we using the term crystalline silica and not quartz?
Great question. It's because there's crystalline silica covers other industrially important minerals. So cristobalite and tridymite are used when you fire diatomaceous earth. So diatomaceous earth, or like kitty litter, is amorphous, but then you, it's opal CT, so it's largely amorphous. And then as you fire it, which they do for a variety of industrial applications, then it becomes crystalline to form cristobalite and tridymite. And so that's why they say crystalline silica, because we have this record of people getting silicosis in those workplaces. That's why they think crystalline silica is not as bad as amorphous silica with the sol gel. But it has, you know, if you think about the number of people in each industry that we're basing the stats off, it's very uneven data.
Yeah, and there's like different experiments too, I suppose, that on rats and things that indicate that the different polymorphs of that SiO2 have different
Toxicities,
yeah,
but none of them agree.
yeah.
Because of course, with anything living, there's all sorts of variables. Like we said, even just the history of where the quartz is sourced from, the size fraction that was used, the types of rats. Rats, you know, rats actually have a different system to like to humans, and they're not sure it actually correlates well. And you definitely don't want to test this on humans. So yeah,
And
it's hard to know.
And it probably, like for the materials that we've looked at, and I think from what most people have otherwise reported, it's dominantly quartz and cristobalite, which are the minerals that are being used in these products. And the cristobalite, I assume, might be used as a kind of a whitening agent because it's like looks a bit whiter. But yeah, that's all we're sort of seeing in terms of that. So that's why we're saying respirable crystalline silica, not just quartz.
And that's what's in the legislation. So all the legislation says crystalline silica to cover those various polymorphs, but exclude the amorphous ones.
Okay. Well, looks like that's all the questions. So we might leave it there. And you know, as all good science is, it feels like we're finishing with more questions than we started with, which is great. And I'm really looking forward to seeing what you come up with in the future. So thank you again, Dr. White, Dr. Tanner, for your presentation again, and hopefully we can hear more about your research in the coming years.
Well, thanks for having us. Thanks
Thank you.
everyone for being here.